So when we're representing or writing a voltaic cell or a galvanic cell, a simpler way to write it is through line notation. Now in line notation, what I do is I write out something that looks like this. My single lines are a phase difference or boundary. So if I notice, it separates magnesium as a solid from aqueous magnesium. On this side, the single line separates aqueous aluminum and solid aluminum. Now the double line in the middle represents either our salt bridge or our porous disk, but this is what separates my cathode and my anode. Now, when I write line notation, it's also very important. I always write my anode on the left and my cathode on the right. If you notice, magnesium is forming Mg2+, so it's going from a 0 to a positive 2. It lost 2 electrons. It was oxidized. It's my anode. Aluminum is going from a 3+ to a solid. It's gaining 3 electrons. It's being reduced. It is my cathode. Okay? So anode on the left, cathode on the right. Okay? If you notice, if I have multiple ions, like I do down here, the single line only separates different states. So my solid is here. Everything that is aqueous goes together. I've got my salt bridge. Again, I've got multiple ions. They all get written together. The single line separates different states. Okay? So when we're looking at galvanic cells or voltaic cells, I have to think about 4 different things. Okay? The cell potential is going to be positive for my galvanic cell. Remember, I can either write it as my cathode minus my anode, or I just change the sign for the one that's actually being oxidized, and it works out to be the same thing. Okay? So I need to know the direction of the electron flow. So I need to figure out who's gaining electrons, who's losing electrons, and I figure this out because I know that overall, again, I have to have a positive E cell. So when I look at my reduction values on this table, the one that was more positive is going to be the one that's being reduced. The one that's more negative, I'll switch the sign because it's going to be oxidized. Okay? I need to designate my cathode and my anode. And then I need to know what state everything is in. Is it a solid? Is it a liquid? Is it a gas? And I need to know what ions are present. Now, in some cases, my ions are the ones that are being oxidized or reduced, and I only have ions being oxidized or reduced. So I've got this reaction up above. ClO3 is being oxidized to become ClO4. So both of my ions are changing. MnO4 negative is going to be reduced to form Mn2+. So it's again my ions that are being changed. Now, in order to make my galvanic cell, in order to actually be able to conduct the current, what I'm going to do is I'm going to have an inert, meaning it doesn't react, conductor. And that's my platinum here. Sorry. Platinum is very non-reactive. It doesn't want to be oxidized or reduced. It wants to mind its own business. So if I put platinum within each of the cells, it'll conduct the electrons as my electrons move from one side to the other, but it won't actually react. So I always need some sort of solid in my reaction to conduct those electrons, the electric current. Okay? So you'll want to change this little thing here, we've talked about spontaneous processes. We said they happen without outside intervention. Whoops, I wrote outside twice, so let's just make that assistance or intervention. Now, this is what you want to fix. The delta G for a spontaneous reaction is negative. The E cell is going to be positive. Okay? Delta G, remember, is our free energy. In a spontaneous reaction, I'm releasing energy, so I represent it with a negative sign. Okay? My E cell is the voltage that's being produced, and so it is positive. Okay? So I can calculate the free energy for my reaction, my delta G, if I know a few things. The N is equal to the number of moles, just like it was in PV equals nRT. The only difference is now, because it's a redox reaction and the only thing I care about are electrons, this is moles of electrons. F is Faraday's constant. Okay? It is 96,485 joules over volts times moles of electrons. And E is my E cell. It's what I calculate for my voltage, my cathode minus my anode. Okay? So here's the way it works. I've got two half cells, aluminum and zinc, and it's producing current. So part A says write the half reactions. Okay? So I've got aluminum. Aluminum, if I look at my table, is going from 3 plus 3 electrons to regular aluminum. And it had a standard cell potential of negative 1.66 volts. Okay? Zinc, if I look at my table, is going from a 2 plus to a solid by gaining 2 electrons. And this was a negative 0.76 volts. Remember, these are both reduction potentials. Not both of these are being reduced. So the one that is more positive is the one that I keep being reduced. So this is going to be my cathode. The one that is less positive, the bigger negative number, is going to become my anode, which means it'll be oxidized. So I can't leave the reaction like this. I have to flip it. So it's going to be Al solid plus 3 electrons. Al solid is going to lose 3 electrons. There we go. And it's going to form Al3 plus. When I flip the reaction, I also have to flip the sign. Now my electrons aren't balanced right now, so that I know I'll need 3 of those. 3 times 2 is 6. I'm going to need 2 of those. 2 times 3 is 6, so that that's balanced. And that's what will allow me to write the overall reaction. I'm going to have 3 zinc 2 plus reacting with 2 aluminum solids. My 3 zinc is going to become 3 zinc solids. I'm going to have 2 aluminum 3 pluses. Now I don't show my electrons here because 3 times 2 is 6, 2 times 3 is 6. I've got them as reactants, I've got them as products. Anything that's the same on either side cancels out. Now my E cell for the voltaic cell is going to be my cathode, negative 0.76 volts. My anode, so negative 0.76 plus 1.66, I get a positive 90 volts, sorry, 0.90 volts. It's a positive because this occurs spontaneously. If I wanted to calculate the free energy, we said that was a negative N times Faraday's constant times E cell. Remember, N is the number of moles of electrons. So this is negative. I have 6 electrons being moved around. Times Faraday's constant. Whoops. 96485 joules over volts times moles of electron times my E cell. My E cell was 0.90 volts. Then all I have to do is multiply. Okay? So when I multiply, I'm going to take negative 6 times 96,485 times 0.90. And what I get is going to be 521,019 joules. This is going to be a negative value. Okay? Or I can say negative 521 kilojoules. My moles of electrons are going to cancel out. My volts are going to cancel out. I'm left with joules. Okay? Now, because this is a negative delta G, I know that my reaction is spontaneous as written. Okay? Now take a second and answer the question in the video. Calculate the delta G for the reaction given. Remember, first you'll have to calculate your E cell and then calculate your delta G.